Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So, anyways, just before I get started, I just want to remind everybody, if I've been chatting in the chat with everybody already, but just as a reminder, don't forget about the onboarding quiz. Let me know how it goes. Maybe I'll ask sometime soon. But I want to remind you where we were last time. So last time I was starting to build up a bunch of terminology that we could use to talk about so-called formal languages. So I ended last day's class with defining what a language is, which it sort of felt like cheating because I was setting up a whole bunch of stuff like about alphabets, strings. I was talking about string concatenation. I talked about, say, sigma star, for example. But I ended off with talking about what a language is. So it's just simply a set of strings whose symbols come from some alphabet sigma. So that's what a language is. And believe it or not, this concept is a core one in this course. So you're going to have to get really cozy with this definition of a language because we're going to use it throughout this entire class. So I want to give you some examples of languages. I'll throw a couple more in here, just to make sure we have an understanding of what this definition means. So I want to first talk about, say if I give you the set of all binary strings that start with 1 at the beginning of each one of their sequences. So here's, for example, a set of strings, a language. So I have 1, I got 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. Notice it's just really just, if I remove the 1 from in front of these, I really have the set of all binary strings just where I have a 1 appended on the front of it. That's an easy way you could see how I could generate all of them to some satisfactory amount. Anyways, that's one example. Another one here is, imagine if I encoded binary strings that represent binary numbers. So imagine I wanted to have a language that stores all the binary strings such that if I read the binary representation of that string, that it's a prime number. So just as an example, can somebody tell me what's this in binary? So, sorry, read me that in decimal. Sorry, I'm getting really excited about this. What is that? Yeah, I've got 2, 3, 5, and 7. Let me just note that down. Very good. So you'll notice I could keep going on and on and on. So like this is 2, 3, 5, and 7. One thing that's worth noting is that you'll take a look at this, and one thing I know I'll throw some students through a loop is that every one of my binary strings here starts with a 1. There's no padding on the fronts of them. So the reason why is because this is just a nice and simple way of representing the prime numbers in binary like this. So just that's a nice little factoid about representing prime numbers using binary, is that if you just simply always ensure that there always is a leading 1, you know that you're dealing with something that's going to look possibly like a prime number, but it may not necessarily be one. So that fact's going to come up in a little bit. So I want to talk about a couple of examples, and I want you to think about them. So here's a couple more examples. Say, for example, if I give you sigma star itself. Is sigma star a language? So surely sigma star has to be a language, right? It's a set of strings, right? It's just an infinitely large one. Just like, actually, technically all of these are they're not a finite size, they're infinite, because obviously we have an infinite number of primes. And of course, this is all of possible binary strings just with a 1 in front of them. So surely sigma star is also a language, it's just really big. I must stress that, of course, this is, of course, for any given alphabet. So you got to remember that sigma star is a language too. And, okay, how about this? Is that a language? That's the empty set. Is that a language? Yes, it's just a set, right? It's technically a set of strings, just there's no strings, right? This is what we often call the empty language. You'll notice all I've done is I've replaced the word set with language. And this is, of course, it could be over any alphabet. So is the notion of a language clear to everybody? So all it is just a set of strings. That's all it is. So it's equally simple, but at the same time, by the end of this class, it's going to feel kind of surreal that I just am using such a simple definition for this thing, because I'm going to start bridging out to other things quite quickly. So let me just move on over here. Okay, so you might ask, Dan, what can I do with this conception of a language? Now, the first one, you may or may not have heard of such a thing, but has anybody ever heard of a membership problem? So if I give you a set, I can ask if an element is in that set or not. You may know this as a type of search problem. So in a previous class, you may have studied things like, oh, I want to search an array and I want to find out if there's an element in there or not, like some key. So I want to take this to the most extreme standard, and I want to ask, if I give you an element in some set, is it actually in that set or is it not? I just want to know if it's there or not. So we can discuss the so-called membership of strings to languages. That is, if I give you a language over some alphabet, if I give you a string W, and remember it's over all possible strings of that alphabet. I want to know if I have L, I want to know if W is an L or it's not an L. Is this clear to everybody what I'm talking about here? So given some string W, I want to know if it's in the language or if it's not in the language. Is it in the set or is it not in the set? So this very simple idea surprisingly actually has a natural correspondence with something that you may be familiar with. I like to talk about this up front because I find sometimes when you hear about languages and all these strings, it's not very intuitive why this may matter. So what exactly can you think of as a problem? It's actually this right here. So when you think about computational problems, very often you think about, okay, I'm given some input from a problem instance, or I have some problem I want to study. To solve that problem, I have to go through every one of the problem instances. I feed it to my algorithm, and it spits out output, and I check if it's correct or not. Something along these lines you may or may not have heard of before. If not, that's okay too. We're going to be building up to things like that anyways in this class. This, believe it or not, is actually a formal way of defining what a problem is. So in previous courses, you may have heard of, okay, we're going to study some problem. Believe it or not, this is actually a nice theoretical but very formal way of talking about what a problem is. Now, if you think about it, there's actually a very special kind of problem that computer scientists tend to be interested in that takes this exact form, just we sometimes label it in a different way. And I'm going to use an example, and I'll let you think about it, but I'll use the example of primality testing. So, of course, primality testing is the problem of testing if a number is prime. Now, you might ask, Dan, how can I describe the numbers that are in fact prime? So I'll write it down for you. we can describe it as the following language. So I'm going to call it L subscript P. Don't worry, it's just a name I'm giving. So it's going to be W. So I'm going to be given some string. It's going to be binary. Now remember, when I take a star like this is just the star operation I talked about last day. Just like I have sigma star, this is sigma right here. So does everybody understand this notation here? Just think that's sigma right here. So I'm just writing it out explicitly, as opposed to saying sigma is equal to the set 0, 1. And I'm just going to say W is a binary representation of a prime number. So imagine I have this language here. Now, if you adapt what I just described up here, I can ask natural questions about, okay, if I give you a string W, I want to know whether it's in this language or it isn't. Now, you'll notice something. Now, I want you to think about this. If the answer is yes, then W would have to be a binary string that whose binary representation is a prime number, correct? So what happens when it isn't? There's kind of like two things that could happen, right? Well, technically it's one, but I'll delineate it into two, just because some people might be like, oh, well, how is this a problem or something? Well, first, there's the natural possibility that W could look like complete garbage, as in, like, it's a string that doesn't actually have a valid binary representation of any prime number. Or it could just be simply it's not a prime number, right? Now, this distinction doesn't make much of a difference for this problem, but for other ones, when we start building up to more complex problems, oftentimes the framework that you may have talked about in a previous course, like talk about problem instances and that, this distinction does actually make a little bit of a difference because we make some assumptions about how we encode the input. So in this possibility, it could be that I'm assuming there's a nice input, like something that looks like an integer that I can interpret in binary in a nice simple way. Or it could just so the big point I'm getting at here, I'm getting really excited about this, is that I can ask questions about whether a number is prime or not by just asking if it's in this set or not. Is that clear to everybody? But there's a fancy name for what I've just described to you. Does anybody know what that's called? It starts with a D. Don't worry if you've never heard of it. Well, that's basically where I'm going. I'm not necessarily decidability, but it's decide something. But it's definitely in that same vein. It's called a decision problem. So what I've just described to you here is a decision problem. So there's a beautiful and elegant correspondence between membership in some language between decision problems. So that's really why when I'm saying, okay, this is basically a problem in a formal way, that's what I mean. Now you might ask, Dan, this definition is not very satisfactory in a couple of ways. One, you may have heard of things called optimization problems, for example. That clearly, like asking questions about like whether it's in a language or not, at first it doesn't look like an optimization problem, right? Or you may talk about, oh, what about sorting? Like what if I have an array and I would like to sort it? Like how does that fit into all of this? Now, the two things. First, any decision problem, like if I have an optimization problem, there's oftentimes a decision variant of that problem. So I can transform a optimization problem into a series of answers to decisions using things like binary search. But I'm not going to go into that much detail at this stage. But if you're asking about sorting and things like that, there actually are ways to frame sorting as a question like this. But I'm not going to go into those details here because it'll take quite a while to do that. So is this clear to everybody? So I just want to make sure that you see this correspondence that exists. So I could talk about I could talk about languages as if they're problems. the big point I want to take from this is that in this course, you're going to find that at the first parts of this course, we're really going to just keep it at this discussion about languages. But towards the end of this class, by the time we get to things that actually have meanings when we encode them, like when I said, okay, well, what if the string looks like an integer that I can easily test? Which, by the way, binary numbers, obviously they have a nice encoding that looks like an integer, right? That's great. But for a lot of other problems, it look like complete junk. So for example, if we're talking about a graph, for example, graphs have a very special way you might encode them on it as a string. So that's what I mean by junk versus not junk. Hopefully that clarifies that. But yeah, there's this correspondence that exists, and I want you just to be aware of it. Keep it in the back of your mind. This correspondence isn't going to come up it won't come up for a while. I just want you to be aware of it. Because as we talk about things in this course, we're going to naturally ask, is my machine capable of recognizing certain languages? And as we build the stronger and more powerful machines, this concept of a language will slowly morph into something more like this. Is that clear to everybody? Perfect. Perfect. Okay, so now what I want to do is I want to give a little overview of what we're going to be talking about in this class, and then we're going to start talking about some machines, which I'm really excited about. That's probably like my favorite thing about this class. So let's do that. So if you're wondering a little bit more about this decision problem and whatnot, I have more discussion about it in the notes. I give a couple of examples of strings that you may give for W and seeing if they belong to that language or not. You'll see it after class, don't worry. So if you find yourself curious about that. Okay, so just gotta get my marker out. Okay, here we go. So just to give you a little bit of an overview of what we're going to be doing in this course, just kind of the big ideas. So the real fundamental question I really want to talk about in this class is really just this. Like, this is like, that's going to be one of the bases of studying theory of computation is, what is that? That's going to be one of the bigger, kind of big ideas of this class. Is how do we mathematically define computation? So we're going to be exploring various different models of computation to address this. That's going to be the first part of this class. So the first part of this course will mostly focus on the study of abstract machines / models of computation. So when I talk about an abstract machine, I'm going to often abbreviate this to say I'm talking about a machine. So I don't have to say abstract machine every single time. I'm going to be saying it's a machine. When I say abstract, I mean it's going to be an exactly defined machine, given exact mathematical terms that it's a thing. And the way it's going to be defined, you can conceivably think about ways you can fix one down and actually implement it in real life. At least most of the models we're going to talk about here have this property. So let's see. So just a couple of examples of types of models we're going to be looking at are so-called grammars. So we'll talk about grammars, for example, in this class. We'll talk about, like I said, these abstract machines, which I'll refer to quite often as automata. Automata, like this. This is plural, by the way. Singular, it's automaton. And by the way, the study of these abstract machines is often called automata theory. So if you're ever wondering what this is called, it's called automata theory. It's the study of these abstract machines. Just to give you an example, I'm just going to draw out a little diagram just showing you an example of one such machine. This is going to come up later. So I want to imagine I have a machine that it's going to operate like a switch. And it's going to have two possible states. Now, how many of you have seen the idea of a state machine? These are things that you will probably have seen if you've taken like a systems class or any lower level course where you have like lookup tables, you may have a state machine. This is going to come up a lot in this first part of this class. This is an example of a state machine, right? So it has two states, off and on. And what I'm going to do is I'm going to describe an action that happens on a given action here. So on a given state, sorry. So I'm going to imagine I start off and I walk over to the light switch and I assume that the light's off. So I start off here. So I start off in this initial state. If I flip the switch, I'm going to toggle it, which causes me to transition from the off state to the on state. So I toggle it, so I follow this edge here. And if I want to turn off the switch, what do? I just toggle it, right? I toggle the switch and now it goes off. I could turn it on and off by performing the action of toggling it, right? So this is an example of a state machine. So the first kind of machines we're going to talk about are going to look like these. So these are, for example, so-called finite state machines or deterministic finite automata. So this is just an example. So the main things I want to kind of emphasize for you is that we're going to have states. There's going to be some finite number of them. There's going to be a starting state, and there's going to be these so-called transitions that occur on a given action. Now the action is going to be, in our case, interpreting a string. And I'll explain how we do that in a moment. But one thing I will point out is that a light switch technically doesn't have a final state or desirable state that the machine would like to be in. It's just either on or off. It's like active. I mean, in real life, you'd have a switch and there's current probably running through to check if it's toggled or not, right? So it'll flow right through. So it's same idea here, but in the machines that we're going to be looking at, we're going to want it so that if we feed a string to our machine, which I'm going to describe how this happens in a moment, we want to have it so it's able to accept the string or reject it. So that's going to be the purpose of so-called final states. I'm going to pin all this stuff down in a moment, so don't worry. So is that clear, everybody? So we're going to be talking about a lot of these abstract machines for a good chunk of this course. So we'll be building up from kind of these more fundamental ones, and we'll be working our way up to the more powerful ones. And eventually we'll get to something that will look like a formal definition of an algorithm. So just it's worth noting, I gave a couple applications in the notes. I'll just make note of them. For dramatic purposes, I have the notes in front of me, so I'm going to dramatically read you them because I think it makes it more fun when I do it that way. So the first one, by the way, I'm not literally reading them. I'm just doing this for dramatic purposes. So first one, if you're familiar with compilers and programming languages, a lot of these machines and these grammars correspond to the design of so-called lexical analysis for compilers. So for example, if you ever heard of what it's called a lexer, these pop up quite often than those. So a lot of the ideas you're going to see here are going to translate really nicely into things that you can actually implement on a computer and have very real applications and things. So I'm not just going to be throwing abstract machines at you just for fun. It's also for fun, but it's also because they have a fundamental bedrock in things like programming languages. Likewise, if you're interested in hardware, a lot of these basic types of machines are things that you can correspondingly implement using things like lookup tables. So anybody that has more of that engineering kind of background might appreciate some of these machines that we're going to be talking about. So just as another example, you might be interested in checking and surveying digital circuits, whether it be for designing them or checking them. You can use a lot of these types of machines to do that. And of course, for dramatic purposes, and this is probably the one, if you were to walk out of this class and say, I'm going to just go into industry and do something crazy, The biggest one I could point out is that later we're going to talk about things like such as regular expressions. Those are used quite often if you want to parse large bodies of text. So if you have a very specific key phrase or a key word that you would like to use, these correspond quite naturally to regular expressions, and they're very usable in practice. There are many, many tools about regular expressions out in practice. We'll be focusing on the theoretical side of all these things and the connections they have with these machines. So is that clear, everybody? So I'm not just trying to have fun with you. I'm also trying to show you things that you might see the ideas translate into things that are very real in programming languages or in applications that you can actually use. So second kind of thing I really want to touch on is, and actually the word came up earlier, is I want to know, what are computers capable of? I want to know what computers are capable of. So at first, and this is one of these things that I honestly separates the computer scientists from the typical practitioner, is computer scientists and a lot of the foundations of computer science are built on questions like this one, historically speaking. Because oftentimes people ask, well, I have a computer, I can do all sorts of things with computers, right? There's so many applications we can use to help people in their daily lives, but there's so many things that you can do with a computer. But the other flip side of this is that there actually are theoretical limitations to what we could do with computers. And that's something that you should be aware of, because one day you might run into a problem and you might ask yourself, does there exist an algorithm that actually solves that problem? This is what number 2 of this is all about. So we'll be addressing the question of decidability. So you might ask, where's this decide part come from? It's exactly what I wrote just a moment ago. It's about this membership question. That's where the decide part comes from. Decision. Think about it like a decision. So, well, so this is one step above that one. That's where number 3 is coming in. This is about fundamental questions about, do there exist algorithms that even solve those problems? There's a third rung, and this is the one exactly that was just pointed out, is what can a computer efficiently solve? What can a computer efficiently solve? So what we're going to be doing is we'll be talking about some theoretical frameworks that allow us to ask questions like this. That if you believe certain assumptions about complexity theory, there actually exist fundamental limits on whether certain problems have efficient algorithms that solve them or not. So there's sort of the idea is that I heard it briefly mentioned. We'll talk about P versus NP in this class. Well, in addition, we'll also, so if you've never heard of P versus NP, don't worry, we're going to be going into it in great detail later in this class. Likewise, I want to know so when you talk about this question, there's going to be 2 main kinds of questions that I would like to know. Are there efficient algorithms to solve problems, so-called tractable problems, so problems that have efficient algorithms that solve them? Typically, we assume these are polynomial time algorithms. Or under these complexity theoretic assumptions, are there problems that are so-called intractable? It says intractable. So there's problems that if you make certain assumptions from complexity theory, and they are pretty well supported by all sorts of neat theorems, but we don't have definitive, yes, there is this thing, but there's a lot of things you can point to and say, yeah, this is the case, but it would utterly shock the entire computer science community as a whole if any of these were wrong. Because there's so many papers published on a lot of these things. Like there's giant frameworks all built around this stuff. Like I work in an area that's very closely related to a lot of this kind of stuff. So generally the question is, do there exist efficient algorithms, or are there these other kinds, these so-called intractable ones? So for example, is the best you're going to possibly do for the running time of an algorithm exponential in its running time? Or is it going to be that there actually are nice ones? So these are kind of the three big pieces of this class. We'll spend a lot of time at number 1, then we'll build up to number 2, and then after that we'll address number 3. Is that clear to everybody? So that's generally what we're going to talk about in this course. So there's a lot of stuff we're going to be going through in this course. So there's a lot of things that you might find interesting. So I'm going to be trying to find something that will at least make everybody excited. So the big thing is that within all of this, I'll be talking about formal language theory that ties it all together. Hence why languages are a core part of this course. Okay? Are we all good to go? Give me a thumbs up. Perfect. So let's get boogieing. Okay, so let's get boogieing. Let's talk about some machines, okay? So the first thing I need to do is I need to talk a little bit about how the machines we're going to talk about first interpret strings. Because ultimately we want to know whether a string belongs to a language or it doesn't. That's going to be one of the most fundamental aspects of studying these machines. So we would like to be able to design machines that are able to recognize certain languages and also figure out if certain strings are able to be designed along with those machines to do certain stuff. Like I said, it's going to be very open-ended but enjoyable. So we're going to be moving in kind of the next big part of this class, is so-called regular languages. So everything I'm going to be talking about in this section of this course is so-called, so any machine I talk about in this class, in this section will be a so-called regular language until we eventually figure out that there are limits to what we could do with the machines we have. Is that clear to everybody? So I'm not going to be trying to do the biggest world-shattering stuff, but a lot of the stuff you can easily use in an application somewhere. So we're going to be talking about finite automata. And I'm going to draw a picture for you. And I promise I have a fun demonstration. I hope it is a little fun. Okay, so I'm going to imagine I have one of these machines, like my toggling switch. So imagine I have my finite automata right here, and it has some sort of way of feeding strings to it. I'm going to imagine it like a piece of tape. So here's W. And imagine I give you a string x1, x2, x3, all the way up to xn. These are going to be a finite string that's provided to the machine. What's going to happen is the machines that we're going to talk about here are going to process them by reading the tape, by pulling it through. It doesn't have to actually look like this. This is purely just an analogy to make it a little easier to see. So the way you got to look at it is like, imagine this pink right here is in fact your string W. And the end of this guy over here on my end here, this guy, as it's fed to the machine, so imagine the string's being pulled in, it's going to read the string from left to right. And by doing so, it's going to cause the machine to switch states possibly. So just like in my toggling switch, there's a possibility that our machine, which will start off in an initial starting state, that as it reads the symbols on this tape, or your string, as it reads the symbols, it may transition to a different state. The machine finishes, yes, question. So excellent question. As a remark, this is actually a read-only tape. So this tape is going to be read-only. That's one big part of this. Also, it's only reading in one direction. So it's only going to read in one direction. It's a read-only tape, if you want to think about it like this. Excellent question, because that's why mainly I wanted to talk about this, because later on we're going to see a machine called the Turing machine, which has a lot of similar pieces to this one. But it doesn't quite have, we don't have that power yet. We're going to assume that this thing has a finite number of states, and it reads the string, a read-only string in. So there's no way you can write anything to this tape. It's just reading the string from left to right. It goes symbol by symbol, reading it, and based on that, it's going to modify the behavior of my machine. So there's going to be kind of two big kinds of these finite automata I'm going to talk about, so-called deterministic finite automata, so-called DFAs. So a deterministic finite automata, the big thing that makes these matter is that they're always in one state. In one state. But there's going to be another one I'm going to call a non-deterministic finite automata. Don't worry, I'm going to be covering these in great detail. It could be in a set of states all at the same time. So just want to make sure you have a little bit of an intuition before I throw the definition of a deterministic finite automata at you. I want you just to imagine I give you W, you read its symbols from left to right, and this is going to cause the behavior of the machine to switch possible states. And there's going to be, the goal here is I want to know whether W is accepted or rejected. So it's got to accept it or it's got to reject it. And we know this will happen for certain once it finishes reading the last symbol. That's all that's happening. Think of it like a ticker tape running through and it just reads each symbol. Is that clear to everybody? So I just want to give you this intuition because I'm going to throw a fun definition at you and I don't want to spook you or anything. Hey, so I'm going to give you, we're going to talk first about deterministic finite automata. These are kind of the first machines I really want to talk about here because, one, they're very intuitive to talk about, but at the same time, they're kind of like the bare essentials of a machine. Why? Because our machines are going to have a finite amount of memory. Their states are finite in their count. And also the other thing is that I've talked about this behavior changing, like my toggling switch. There's going to be a finite number possible of these. So it's going to sound like something ideal that you might think of as a state machine. So let's talk about a deterministic finite automata. Finite automata. Just as a reminder, I probably said it a couple of times mistakenly. Singular for automata is automaton. Plural is automata or automatons. I have to usually say that because it's such a cool word. Okay, so I'm going to abbreviate this as DFA. Why? Because if you wrote this out 20 times, I'm sure your hand would be like, oh, just please stop. So here we go. Like I said, I'm first going to present the definition to you. We're going to use it to see how the machine works. And then I'm going to give you a couple of ways you could represent the DFAs in a way that actually is very easy to understand. Just like our toggling diagram I had before. Does everybody understand the game plan that we're going to be doing? So I'm going to present this definition. Don't feel intimidated by it. I just warn you. At first it'll look intimidating. But it's okay. So it's going to be a quintuple. It's going to be, so that means it's a 5-tuple. It has Q, sigma, delta, Q0, and F. See, I said it was going to look a little bit daunting at first. Where where we have the following. So Q is a finite set of states. Oh, my turtle fell. That's okay. I'll go get him after. Finite set of states. Poor turtle fell down. Is a finite set of states. Sigma, you might know what sigma is right away. That should correspond to your alphabet, right? Is a finite non-empty set of input symbols. Now the next one, this is the one that you'll find that we'll have a fun time describing. Delta is a transition function. That takes as inputs / arguments a state and a symbol then returns a state. So formally, if you're wondering what this looks like as a function, I'm saying delta is going to take as two parameters a state and a symbol, and it's going to return me a state. So that's what a transition function is. I said that this one's going to be the doozy that we'll see plenty about next time. So Q0, which is going to be one of the states, is a start state or the start state. There's only one. Is the start state. And then we're going to have a subset of all these states that we're going to call the final or accepting states. So this is so F is a subset of Q, is a set of final / accepting states. So there's the definition of a DFA. So now this is where it gets fun. You'll notice that it only stays in one state at any time. So the way it's going to work is, and I'll define formally how we compute the current state. But you'll notice there's no variable here or anything I said that, oh, the current state is stored in a variable or something. You'll notice that it's just that this machine is going to be in a state at some point. Now, in an implementation, you could keep track of this easily, which that is actually how you would do it in practice. However, you can actually compute this using a so-called extended transition function, which I'll define probably in either next lecture or the lecture after that. But right now, we're just talking about the specifications of the machine. So the big thing here with the DFA is it's in one state at any time. It's not a set of states, it's just, well, technically a set of states is just one, but my point is there's only one state it's in. It starts off in the start state, and as we read the string, it's going to get fed to this transition function, and it's going to modify the state of the machine. So I feed it the current state, the current character or symbol of my string that I've read, and it's going to give me which state I need to go to. So I'm going to do an example just to really kind of, yes? Yes. Okay. So let me just demystify it here slightly. So in my off-on example, it would start off at Q0. Q0 would be my off state, would be off. Then if say these strings were just toggle, like a symbol that represented toggle, if I read a toggle, it will move me to the state that is on. So it can move between two different states, on and off. But you'll notice in my example, I never had a final state. So I'm gonna give an example just so we can see this definition. I think that'll be basically the rest of this class, because we only got a couple more minutes here. So I'll do an example here. First, this is gonna look really abstract. Don't let it get to you, okay? I know the first time I seen this definition, like, I thought it was kind of cool, but it does look a little intimidating if you've never seen like tuples of things that look like this before. Don't worry, it's very intuitive once you see the couple ways we're going to visualize these machines. It'll be very much like our toggle example at the beginning. So here's just an example. So I'm going to define a DFA M1 like this. And I imagine I have my set of states being S0, S1, and S2 like this. So this is my set of states. This is Q. This is Q right here. And I say 0 and 1. This is sigma right here, right? Then I have delta. I'm going to define that in a moment. Then I'm going to have S2. S2 is going to be my start state, so you can think that's Q0. Often when you define these, you often will try to use like subscripts with Qs in them. This makes it a little easier to read, but I just want to, for the sake of showing you multiple examples, I'm going to use different symbols just so you can see it. Because don't worry, it's just symbols. They're not... And say F... This is F here. It has two states that are so-called accepting or final states, S0 and S2. Sorry, S2. It should be S2. Okay. So I'm going to write out the transition function. And you're going to see first this is going to look really, really just unintuitive at first. But next class, I'll show you how to write it in a very intuitive way that's really easy to see and picture for yourself. So you could actually watch and do it yourself. Because at first, a lot of these symbols, they look really cryptic. That's part of it's a feature of this area, but it can be a little bit daunting. So so remember, delta is a function, and notice that I define it, so I have to define a transition for every single one of my states and for every symbol in the alphabet. So my input symbols. So I have S0, so I have to define each one for S0, S1, and S2. Each one's going to have it paired with the input symbols. So I'm just going to define this here, and this will basically be where we're going to wrap things up. So you just copy this out. I'll have it in the notes as well. But I just want to make sure you get an appreciation just to see what this looks like formally. Because I'll be moving to the more convenient way after this, because you'll say, hey, look, Dan, that looks much easier to do. Let's do it that way. S2, 0, S1, and delta S2, 1 is S1. So you'll notice that for every single state and every single input symbol, I've defined a transition. The way this works is that if, say, for example, my current state is S0, if I read a 0, I go to state 1. But however, if I encountered a 1, well, in S0, I stay in S0. So what's going to happen is, imagine I give you a string W. This is just me giving, whoop, I wrote it a little too high. There we go. If I imagine I give you a string W, and say it's like 0, 0, 1 like this, I would start off in S2. So I would read this guy right here. I would say, okay, if it's in S2 and I read a 0, because I start from the left, I read a 0, I go to S1. So that means I'm currently in S1 after I make the transition. Then I would read 0 again. So I would be in S1, I read the 0, I go to S0. So now I'm currently in S0. And then I read the 1. 1 in S0 goes to S0. So the question I have for you, S0 and S2, these are final states. I'm going to tell you that a string is accepted if the current state is a final state. Does that mean that W is going to get accepted by this machine? Yes, because it's going to be an S0 when it's done reading the string. Exactly, exactly. So this is actually a perfect place for me to stop. I apologize for going over a couple minutes here. So next day, we'll come back to this example. I'm going to show you a couple of different ways you could represent this DFA, and also be talking a bit more about what we could do with DFAs. So we'll do some examples where we actually design some DFAs that do fun things like recognizing substrings in a string. So that being said, I want to say thank you very much, and have yourself a beautiful day. I'll see you later.